called in Spanish Cuantileros, connected today, Karl. This is a weekly seminar where Quantil usually brings experts to talk about different issues, basically in programming and mathematics. So today is my great pleasure to introduce my colleague, Karl Warburton. He is one of our experts in reconstruction and deep learning in the NOVA experiment that happens in Fermilab. Karl is one of the leading experts in these topics of image recognition and deep learning in the field of particle physics, and he's currently in charge of the, he's one of the conveners of the reconstruction and deep learning research group in the NOVA experiment. So thank you, Karl, for being here with us today, and please have the floor.
Cool. So I'll turn my video on so that you guys can actually see what I look like. Let me see, where am I? Here. So yeah, thank you very much for that introduction. Well, I should say, from the start, like, this should be as interactive as you guys want. So if I say, if you want to ask a question about anything, please, feel free to interrupt me. So yeah, just expanding on Enrique's introduction a little bit. I'm from Stoke-on-Trent, which is a city right in the middle of the UK. I use machine learning to improve their studies that I perform, looking for neutrino oscillations. So I'm aware, most of you probably don't really know what that is. So I'm going to spend, a little bit just, presenting the idea as to, how neutrino oscillations work, to give you, a feel for the motivation for what I'm going to talk about. I did my undergraduate and PhD at the University of Sheffield in the UK. So it has the world's oldest football team there. I worked on simulations as well as reconstruction techniques for a prototype detector for the next generation of neutrino experiments. So Dune, which I'm going to mention at various points throughout this seminar. I'm currently working at Iowa State University, based at Fermilab, where in addition to the work that I do on NOVA that Enrique was mentioning, I work on supernova triggering in Dune, and I'll speak a little bit about how machine learning may be able to improve the current methods that we have for doing this. So, just a brief outline of what I'm going to talk about. So, I'll quickly, say, what are neutrinos, because I'm aware, most of you probably aren't too familiar with the idea of neutrinos. And then, what we try to fundamentally do in neutrino experiments. I'm sure most people are, are aware, but, I'll give a brief introduction to machine learning and how it works. Then discuss the challenges of applying machine learning in neutrino experiments, and then quickly just mention some of the future opportunities as to how, machine learning techniques can have, nice synergies between, industry and particle physics research. So, just to start off, a crash course in particle physics, just because, as I've said, I imagine most people aren't thinking about this all the time. So, from, high school, science, probably remember that, everything is made up out of atoms. Atoms are made up of electrons, which orbit a nucleus. The nucleus is made up of protons and neutrons. What you may or may not have been taught, so, depends very much on schooling, is that protons and neutrons themselves aren't fundamental. They're made up of things as well. They're made up of things called quarks. So a proton is 2 up and a down quark, and a neutron is 1 up and 2 down quarks. And this results in them having their charge of, +1 and 0 respectively. Electrons are fundamental and stable, so, the things that orbit the nuclei, but they have counterparts, which you're very rarely taught about in normal schooling, called neutrinos. They're rarely discussed because, really they don't do much in sort of everyday life that we have that we experience, but they have very, very profound implications for the universe. So then, everything that, exists in nature that we interact with, all the time is in this, first column here, However, when physicists, go out and test theories, we actually discover that there's 3 generations, they're called, of particles. So you have, higher complements to, both the up and down quark, so the charm and strange and the top and bottom. And then there are heavier versions of electrons called muons and tau particles. And then on the right here, this is all the force carrying particles. And you may remember back in 2011, there was a lot of excitement when over at CERN, they discovered the Higgs boson. So this is, how we think every particle in the universe gains its mass. And this entire thing here is called the Standard Model of Particle Physics. And I'm going to sort of put that to one side for now. But it's sort of the most successful theory that mankind has ever come up with. Everything that we throw at it, so all the experiments that we do, come up, pretty much exactly what this predicts. However, we know that it's not complete. So it doesn't explain dark matter, which you may have heard of. It's how we know that galaxies are held together. It doesn't explain dark energy, which is that we see that the universe is expanding faster and faster as it expands, which goes against our theory of the Big Bang, where really the acceleration should be slowing down. It doesn't fully explain the matter-antimatter asymmetry in the universe. So from the Big Bang, matter and antimatter should have been made in equal amounts. However, we're here, so that clearly wasn't the case. And it doesn't explain so-called grand unified theories, where we try to unite all of these forces into a single force at really high energies. And it can't really manage any of this. Yeah, Andre, I see you've raised your hand. I can't hear you if you're trying to speak. Okay, I'll carry on, but if I'm not sure why I can't hear you. Yeah, if we figure out.
Yeah, Karl, go on and we see if Andres has a question later on.
Okay, cool. Yes, in addition to all of these these things, it really struggles to explain the properties of neutrinos, which is what Enrique and I spend our time researching. So just a little bit more information about these neutrinos. So if you arrange all of these particles so these are things that we really ways that we know that neutrinos are really strange. So this unit here is a mass scale. So we'll ignore what exactly an electron volt is. But I've just tried to put images here of things that are more relatable to us. So this right hand side here is about the scale of a feather. Things up here are the size of a ship. Things up here are the size of a skyscraper. So most of the particles are sort of large animals like polar bears to military ships. So they're pretty heavy. Whereas neutrinos are the scale of a housefly to a feather. So there's a huge dearth of particles that have the mass of us basically, and we don't really understand why that is. The standard model really can't explain it. And also another strange thing is that neutrinos are the only fundamental particle that aren't charged, don't have electric charge. So all of these particles here have either integer or 1/3 or 2/3 charge, and why that is a bit strange. Neutrinos also just don't interact with anything basically. So a neutrino would quite happily pass all the way through the sun without many times over without interacting. Whereas most particles and electrons and things are stopped by relatively thin materials, say 10 centimeters of something will cause all of these particles to interact. And why that is a bit strange as well. And there's a t-shirt here, but just to show just how numerous neutrinos are, 10 billion of them. Well, actually, wait, no, I always forget what number this is. 10 trillion maybe neutrinos pass through sort of 10 centimeter square every single second. You know, they're just everywhere constantly, but you know, they barely interact, so it makes them really hard to study. Another like strange quirk of neutrinos is that there's something called mixing. So this means that they don't exist as the electron, muon, tau flavor states. They actually exist as superpositions of these in so-called mass states, U1, U2, U3. So the full explanation for this is, you know, is quite complicated. But if you just take my word for it that, you know, this mixing occurs, by studying how neutrino oscillations occur, which I'm going to cover in a second, we know that, you know, the ordering of these masses is either sort of the nu3 mass state being the lightest or the heaviest, but we're not sure why. And if it turns out that this nu3 mass state is the heaviest, that would show, you know, some very strange symmetries in the universe that we can't currently explain. You know, we have some handles on these different masses, but we don't know the exact structure or the exact values of them. And then, you know, in relation to the mass, there's also another strange thing of it's possible neutrinos actually get their mass in a different way than all of the other particles through it's a process that's forbidden in the standard model called Neutrinos double beta decay, where 2 protons turn into 2 neutrons. You should get 2 electrons coming out as well as 2 neutrinos, but there's a chance that they're their own antiparticle, and so you don't. So I apologize, this is quite a lot of physics. I just wanted to sort of give you an idea of like the amount of things that we don't understand about these particles, and that sort of feeds into all of the experiments that we do. So neutrino oscillations are, you know, I find particularly interesting. To imagine we have a cluster of neutrinos, so they're all blue here, nu alpha, and you know, there's 1 nu beta in this package. We then fire them a distance L through the Earth, and after that time, most of the nu alphas have now turned into nu betas. So you can see here on this graph on the bottom that, you know, the probability of having the nu alpha has decreased, and the probability of having a nu beta has increased. So then if we fire them another distance L2 through the Earth, we get back to this initially pure nu alpha state. And, you know, so just sort of thinking about this is very, very weird, right? It basically means that, you know, I could be sitting here and I'm me. You know, I walk to my kitchen that's, you know, just behind this wall, and, you know, I've turned into somebody else. And, you know, I walk down the stairs and I've turned into someone else again. This is very, very strange, you know, for us to picture. But this is, you know, just how quantum mechanics works, basically. So the presence of a third mass state makes this a bit more complicated, but it's effectively the same. So, you know, sorry about all that. I just wanted to, you know, again, just present some of the physics behind all of this. So neutrino experiments are really complicated. So we have to build them in lots and lots of different ways. So, you know, we have detectors that are made out of metal with, you know, different materials in them. We have, you know, detectors that are built on the Antarctic ice, you know, almost 3 kilometers underneath the ice, and, you know, much, much bigger than the Eiffel Tower. We have, you know, small detectors that have, you know, filled with gas, and then we record flashes of light. You know, we have experiments that are, you know, filled with liquid scintillator. Nova that Enrique and I work on, an easy way to visualize it is that you have drain pipes filled with baby oil. Then we have other experiments where we fill them with liquid argon, which is a noble gas, and it becomes liquid at minus 200 degrees Celsius, and we apply electric fields to that, and we, you know, we get really picturesque images out of the detector. You know, we also are looking at things over huge ranges of energies. So, you know, if we go back to this electron volt that, you know, again, we're not going to worry too much about what it means. Nova looks at, you know, 5 billion electron volts. Katrin, which is trying to determine the absolute masses of them, is looking for, you know, this tiny, tiny difference here of, you know, the order of 1 electron volt, you know, 1 billion times more fine resolution than Nova's looking for. You know, it's looking for this very slight deviation here from the red to the blue lines. Next is looking for this tiny, tiny spike here, at the end of this long tail distribution. IceCube can detect PeV neutrinos. I forget the exact number that PeV represents. I think it's 10 to the 15 or something. So, neutrinos interact over a wide range of energies. So, we have a huge range of detectors, we have a huge range of energies, and we have a huge range of different topologies that we're looking for as well. So, you have, if you look at, these interactions here on the left that we see in NOVA, you'll see they're very blocky, whereas here on the right, from microboom, they're, much more intricate. And, this distance here is 7 centimeters. This distance here is a meter. Here, you're on the scale of millimeters. Again, here in IceCube, you're on the order of, tens, if not hundreds of meters. So, neutrinos are very, very interesting. There's lots of things to study about them. The detectors that we have to build are, hugely varied, and we, use lots of different techniques to do this. So, apologies that was quite a lot of physics. But I really wanted to set up the idea that, neutrinos are really interesting, and
sorry, Karl, I think there's a question.
Yeah. Diego.
Yeah, thanks. I was wondering what that peak in that this energy distribution means, and I hadn't heard about the next experiment.
So which peak?
The one that you mentioned about the next experiment.
So next looks for neutrino double beta decay. So it's this idea that you have. Let me see. I want to go back here. So you have 2 down quarks convert to 2 up quarks. So it's actually neutrons to protons, and you have emitted 2 electrons and then potentially 2 antineutrinos. So because of the what do I want to say? The material that you use to measure it, you often get you can get 2 neutrino double beta decay, where you have 2 electrons emitted, and because of the continuum distribution that you get, you're going to see this peak here. So you have 2 neutrinos, and they're likely to take away some of the energy, as well as the positron, the electrons or positrons that you get emitted. And so just from energy conservation, you get this sinusoidal function, or this Gaussian function. But then if you have neutrino-less double beta decay, all of the energy goes directly into the 2 electrons. And so when you measure them, the energy that they have will be exactly equal to the energy difference of the nuclear state. And so they'll have a very, very fine energy of, 2.47 MeV in this case. Does that make sense?
Yeah. So then you would study this process in order to look at the energy difference, and that would tell you something specific about the neutrinos in this case, like something related about the difference in their masses, or?
Yeah, so we look for this in order to, so if we see this peak here, that means that neutrino-less double beta decay can occur. And if neutrino-less double beta decay can occur, then neutrinos are their own antiparticles. Then they are so-called particles. So it's like a 2 or 3 step thing that you get by observing this peak.
Yeah, I see. Okay. So yeah, so that's basically also like trying to prove to check if this process does occur.
Yeah.
Okay, yeah, I see. Okay, great. Thanks.
It's okay.
Yeah, thanks.
Any other questions? I know there was a lot of theory there, so I mean, anyone who's interested in all of this theory, feel free to ask. Cool. Right. So now just, to give a brief introduction to machine learning. So, there's lots of different ways that, we can go about having machine learning. So, they're sort of, all lined out here briefly. The basic structure of an artificial neural network or a deep neural network is that they're basically just a large collection of interconnected neurons. So here on the top, I have, a schematic of a neuron. So, it has some sort of input. It can have many inputs. Then it, performs some sort of mathematical calculation, often an activation function. And this calculates an output, which can then either be combined to the final output, or can be an input to the next layer of neurons. So here is one neuron, and then here on the bottom I have sort of a simple schematic of how you build that up to have a fully connected network. So you have a set of inputs, that they are then all passed to this first layer of neurons. So, you can see this blue circle here goes to all 4 of these neurons. They perform these activation functions, these activation calculations. They then get passed to the next layer, where you can have an arbitrary number of hidden layers, until finally you have your final layer where you get all of these input weights, and then they get passed on to an output, which is often some sort of score for something that you're looking for. So, in this case here, you're trying to identify what this interaction is here. As you have all of these red dots are hits. You can take the length of this blue circle, the number of hits in the entire images in the entire image, the energy that you calculate somehow for this blue circle, pass it through the network. It performs a bunch of calculations on all those parameters, and then it tells you in the end this is likely an electron-neutrino interaction. So the inputs that we use here are often calculated using traditional reconstruction methods, and then we use a neural network to combine them all to figure out what the interaction itself is. And it's worth noting here that the network doesn't necessarily learn why inputs like length and hits and energy are correlated. It just learns that they are. So it sort of doesn't necessarily learn what interaction topologies are. It just learns how different factors are related to each other. So, all of these techniques were sort of really developed already in the 90s, and neutrino experiments have a long history of seeing stuff that's being developed and applying it to their physics. So here I have one of the very first DNNs that was applied in neutrino physics by the SNO experiment. So it didn't actually achieve better separation than the traditional methods were able to do. So it wasn't used in their actual analyses, but it showed that it was possible to do, and really laid the groundwork for these techniques to be fully explored, to the point that now most analyses feature neural nets in one way, shape, or form. So modern, a lot of the modern applications use convolutional neural networks. So the premise here is that you pass the network an image or a pixel map of what you're looking to identify, and you allow the network to extract the features rather than pre-selecting them yourself. The argument here being that it removes any bias which you may introduce from the traditional reconstructions. And in practice, this means you cast these images into the signals into images, and then you pass it to the network. And the networks consist of convolution layers where you step through the image and perform a bunch of calculations, and then these get passed to pooling layers where you aggregate down from the convolution layer, and you then have many iterations of convolution layer to pooling layer to another convolution layer to another pooling layer, until eventually you have a fully connected layer at the end, which looks naively similar to the DNN that I was just discussing. And you traditionally use an image to RGB tensor strategy when you transfer things from the input image to the first convolution layer. So, just stepping through these processes. So convolution layer, you have some sort of mathematical function here, where you step through different pixels. So, for this result here, where you end up with 5, you do 75 times -1, 80 times -2, 80 times -1, and then 80 times 5. Well, 80 times 4 here on the bottom, and you end up with a number 5. And you step through this, going all the way along the pixels, performing all of these calculations. You often have many different convolution filters in a single layer. So then the pooling layers, these downsample the image, thus reducing the computational cost, emphasizing some of the features that you draw out with this step. In this case here, it's just a max pooling. So you take the highest value in each of these colored squares, so 6, 8, 3, and 4 in this case, and then you would pass that then on to the next convolution layer, which is the layer down. Why is machine learning becoming so popular now? And it's really because there's been a huge growth in computing power over the last decade, particularly GPUs. And this is at the same time networks are becoming much more accurate, whilst also requiring much fewer resources. And this is particularly important because some future experiments are going to record the order of 30 petabytes of data a year. So now stepping through some of the challenges in applying machine learning. This all really started with one of the first CNNs, which was GoogleNet, which was developed for the 2014 ImageNet Challenge. It took defined pictures of flowers, elephants, pumpkins, and people developed networks to classify these. And GoogleNet was blew everything else out of the water by having the first non-sequential implementation of convolution layers. What I was just talking about. And neutrino experiments have tried to implement this with as few modifications as possible to begin with. So one of the first applications was in an experiment Next. So here they designed a network to perform background rejection for neutrinos double beta decays, and they developed both a network that had quite a coarse voxelization, so where each of these voxels here is 10 by 10 millimeters, as well as a finer voxelization that was 2 by 2 millimeters. They took 2D projections of the detector readout, so YX, ZY, and XZ, and used that as the RGB input for their network against charge. And when they did various studies on signal and background rejection, they found that the network, just simply by taking GoogleNet, outperformed their traditional reconstruction by between 20 and 60%, which is a huge increase from literally just taking an industry application and applying it to their data. So Nova, because of the structure of our experiment, we have two decoupled views. So we have readout planes that are vertical and readout planes that are horizontal, stacked one behind each other. This meant that we couldn't just combine them in the way that Next did. So we had to develop a Siamese structure where we take the hits from one view on one side and from the other view in another tower, and then we perform the various calculations, and then we merge them right at the end in a fully connected layer. And when we first used this technique in 2017, we found that it increased our effective exposure by about 30%, which is a huge increase. It was also the first CNN to be used in a published particle physics result, which is quite fun. And since 2017, we found that training sign-dependent networks is very important. So training a network for neutrino and a network for anti-neutrino mode. Because we have we run in two different modes, one where we record neutrinos, one where we record anti-neutrinos. And we found that doing this can increase the effective exposure in anti-neutrino mode by up to over 10%, which again is extremely important. So other experiments have have different detector geometries. So Kamland-Zen is a sphere and basically has a balloon hanging in the middle of a different material. And if they were to just try to do 2D convolutions straight from their readout, you end up having quite severe distortions because your detector readout, isn't uniform, in a 2D space because it's a sphere. So they, as such, they had to use spherical CNNs, where you extract the angles using Euler angles and SO3 convolutions. It scans the whole phase space, and by doing this, you avoid distortions. And their spherical network achieves better background rejection than their 2D traditional algorithm by about 10%. So this is just showing that you have to really tailor your algorithms to the particular problem that you're trying to solve. And IceCube, also saw this, but had to tackle it in a different way. So IceCube, as I said, is in the Antarctic ice. It's a huge detector. So I forget exactly how wide the spacing is here, but it's the order of 100 meters, and their readout is very ununiform. So you have a very dense part of the detector in the center, and then it becomes much more spread out as you escape that, as you go further away from the center. And so that means that you really can't use traditional CNNs to map their detector phase space. So instead, they use graphical neural networks, where the nodes define an element of the detector, and the edges show connections between the different elements. And this shows that it's ideally placed to mitigate some of the aspects of IceCube data. And so I always really like the IceCube events. I can't really tell what they're showing, but they just look very cool as these big bulbous things. And so their graphical neural network, it had identified 630% more signal, and had a signal to noise ratio that was 3 times higher than either their traditional CNN or traditional algorithms. So the CNN and the traditional algorithm were found to have very similar performance. However, by moving to these graphical neural networks, they found a huge increase in the performance that they were able to achieve.
Sorry,
so,
Karl,
yep.
Do you mind clarifying what you mean by backgrounds?
So sure. So they were trying to separate neutrino events. So I think this was primarily in their well, they only study atmospheric neutrinos, right? So they were trying to separate atmospheric neutrinos from cosmic induced events. So cosmic rays, come in, the side of the detector and produce huge showers, which can look very similar to the atmospheric neutrinos. So they were trying to distinguish between the two. Does that clear it up, or do you have to more?
I don't know if someone else has a question about that. I just wanted to make sure that we all have the same definition of background.
Right. Yeah. Oh, so I guess, I didn't really cover this as well because the experiments are so varied. They all have different definitions of background as well. So, they all have different definitions of signal. So, nova, we create a neutrino beam, and we have we know to a very high precision when we expect these neutrinos to come. And so we look in that window, and we very clearly looking for a neutrino in that at that time. Now we record cosmic rays because nova's on the surface, and so we need to reject all of these cosmics that come into the detector. And we employ our networks to do that. Experiments like IceCube are recording atmospheric neutrinos, which just come into the detector all the time. So they can't use this timing resolution to determine stuff. But again, they're trying to combat cosmic rays, and you use, well, you can, to some extent you can use directionality, but not really, because atmospheric neutrinos can come from above or below. Some of the double beta decay experiments, they're particularly worried about radiological backgrounds. So, they're looking for, very, very low energy signals. And so, you're worried about radioactive contamination in your detector. And, they're looking to try to distinguish, the signals that they get from a neutrinos double beta decay from a radiological background. And, they both look very similar. So yeah, there's a huge range of signals, there's a huge range of backgrounds, huge range of energies, huge range of technologies. So, you can really find any sort of problem that you may want to have exist, you can probably find it somewhere in, applying neural nets to neutrino physics. Yeah, so then, the next challenge, I'm going to talk about, a little bit about this now, is quantifying network bias and uncertainties. So, humans, we can look at these images and know that, none of these animals should exist in nature. Dogs don't have some weird cone on them. Giraffes don't look like a guitar. Penguins and dogs aren't, mixed, and anglerfish just shouldn't really exist, which is why they're at the bottom of the ocean. We need to make sure that our algorithms, know, that these three are not real animals and this animal shouldn't exist. The danger of, not being able to quantify this bias and uncertainties are that, we could, inadvertently train our networks to, not understand, the full context that various things can exist in. For example, if you take, here we have two images of cows, one sitting in, a lovely alpine field, and one running along, a beach. If you only train your network on, cows sitting down in alpine fields, it will, as is shown here, very correctly identify that, there's no person, there's water, there's a beach, but the network, may not realize that, this animal thing that it's, clearly identified as an animal, but it hasn't identified that it's a cow. So, you need to make sure that, you train your networks on, the full range of things that it might be exposed to. This is particularly susceptible for CNNs because, you're passing it the image. So, if you present it an image that doesn't look anything like the training data set, then it can get really confused. And so, we particularly worry about this in particle physics because we train our models on simulated data where, we make a bunch of assumptions going in about how the simulated data relates to the real physical data. You also make assumptions in selecting your training data set. And, one complication for all of this is that we know simulation will never fully produce the real data. And, worryingly, this is a well-known problem, but there's no standard or complete techniques to address it. So, as a whole community, we need to work on improving this. So again, now just stepping through some different experiments where they've tried to confront this challenge. So XO200 is another neutrinos double beta decay experiment. They designed a network to perform charge-only energy reconstruction, and they trained it on a simulated calibration source in the center of their detector, thorium-228. And if you can just about see the black line on this plot, this was the true energy distribution that they trained on. But then after doing the training with just the pure thorium-228, they found an artificially high energy resolution. So, you can see it's very clearly peaked here. And, that was concerning because, it means that it's, preferentially identifying this energy range. And, you then can't be sure that, when you start using other elements that, will behave correctly. So they found that by training on a simulated calibration gamma ray source in the center of their detector, they were able to remove this unusually large improvement in the energy resolution, because this green line is unphysical because just the true distribution isn't this sharply peaked. So they used a more uniform training, and then they tested it. They got the correct looking energy distribution, and they then repeated this check with different calibration sources throughout the detector. And again, they found that this uniform training gave much more consistent results. So they eventually went with this uniform training rather than the pure thorium-228 training. Another key way of measuring bias that physicists are particularly worried about is because of our training on simulated data versus real data, is quantifying the biases that you may introduce by doing that. So Minerva developed a domain adversarial neural net. So you have your input. You have at the top here your more traditional looking neural net, where you perform convolutions and feature extraction, and then you perform the interaction identification here. But they then also added a domain classifier, where the network here is trained to learn the differences between simulation and data and discourage learning about those differences. So this is done by a gradient reversal layer, which you can see here, and back propagates the loss function here. I think that was what I wanted to say there. Yes. There's also then ways to measure the bias that you have in your training, quantitatively. So we do this in Nova via a process called muon removed electron added. So what we do here is we take simulation and data muon neutrino interactions. We identify the muon, we remove it to leave only like a proton or a pion here. And then we simulate an electron with the same energy as that we identified this muon with into the detector, and then we try to identify this proxy of simulated and data event to check that our network is identifying electron neutrinos as accurately as we would hope. And this is partly because in data, because of how our neutrino oscillations occur, we don't have very many electron neutrinos in our far detector data. On the right here, you can see a plot comparing the reconstructed electron neutrino energy for both data and Monte Carlo. And you can see that they agree very, very well. And this shows that our data augmentation and our network response is very similar between data and Monte Carlo. This year, Nova introduced another technique that's very similar to this, where we identify cosmic ray muons that decay in the detector, and we identify the resulting electron that comes out of that decay. And again, we found that the network was behaving as we would want it to. Finally, there's also, you can try to compare how the network performs against humans. So, obviously, it's too intensive for humans to sit there and identify every single interaction that they're seeing. But, you can make a human labeled data set of, a couple of thousand relatively easily. And, you compare the identification efficiencies for, that data set between the neural net and the humans. So, I can look at this interaction here and quite clearly say that on the left is an electron neutrino, because you have this electron shower, whereas on the right this very long straight track is quite clearly a muon. So, obviously you can do this in both data and Monte Carlo. In data you can't know the true state of the interaction, but you can compare them to get a good guess. In simulation, you have the truth that you can go back to. So very interestingly, it was found that humans and the neural network disagreed for about 2% of the interactions, as well as 2% of the particles when they eventually trained a network that tried to identify the individual particles. So a proton or a muon in this case. One more thing as a way to quantify bias. So a lot of neural networks tend to give you fixed weight distributions. They just give you one score for, well, they give you a score for the different outcome probabilities, possibilities. However, instead you could have a probability distribution as your network output using Bayesian neural networks. So here you replace the fixed value weights with probability distribution functions, meaning that the output is then a probabilistic function which you can interpret as a most probable value. So this means that you're much more accurately able to convey a scale of uncertainty in the network outputs, and this is particularly useful when the predictions are outside of the scale of the training data set. A third challenge is actually interpreting what your network is telling you. So the shorter a network is, sort of the easier it is to be able to interpret what it's doing, particularly for the case of DNNs or ANNs versus convolutional neural nets, where the exact kernels, what each kernel is doing, we can sort of figure out, but how they combine as an entire structure to form the weights is really almost impossible to do. Again, physicists are particularly worried about this because we want to relate the known network features to underlying physics phenomena, in order to minimize or correct network inefficiencies, and also to try and figure out specific interaction topologies that the network is using to perform its identification. So, one example is if it's really doing very well at identifying muon decays, you want to check that it's looking for the Bragg peak that you see right at the muon decay. So, there's a couple of ways to try to figure this out. A widely used technique is to make so-called t-SNEs. So here you take the multi-dimensional space where networks perform their identification in, and you transform that down to a 2D space using nonlinear transformations. So this preserves the separation between points, just at a lower dimensionality. So here for this t-SNE here from Dyer Bay, you can see that this purple region here is very clearly distinguished from everything else, as is this red block over here, which are from their so-called IBD delay decays. So I forget exactly what they are, but you can basically see that it's very clearly identified that this structure of events is very different from this structure of this cluster of events or this cluster of events. And other ways of trying to do this are to perform principal component analyses. So here you make vectors along dimensions of maximal variation in the data. And this is particularly useful because the vectors are always orthogonal to each other, so at 90 degrees to each other. You normally perform this on the input data to reduce the number of inputs that you have to use. But you can also do it on the extracted features to reduce dimensionality for visualization in a similar way to a t-SNE. It's also possible to identify features which are important to CNNs. So you can do this by hand, simply by covering up parts of the image and seeing whether the network is able to classify the image with the same score, with the same efficiency. That's a process called occlusion testing. You can also ask the network to make salience maps where it tells you what features it's using to make the determinations. And here on the right, you can see that for this grasshopper, it's very clearly identified the grasshopper, and you can see where the density of the pixels are that it's using to make that determination. Excuse me. So here for this goose swan thing, you can see that it's quite heavily focusing in on where its eye is. Yeah, and that can be very useful for determining how your network is learning to do these identifications. Another challenge is just the raw computational and systematic constraints. As we all know, machine learning uses huge amounts of resources. neural nets, even though they're becoming more efficient, they still perform many floating point operations. And traditionally, within particle physics, a lot of our evaluation has been done on CPUs, making particular use of the Open Science Grid, which, as you can see here, has clusters all over the world. However, a similar partner for GPUs doesn't really exist, and so this is a fundamental problem for rolling out widespread machine usage of machine learning algorithms. Small GPU clusters are relatively inexpensive. They're really only suitable for training, and so we need these large-scale GPUs for performing actual evaluation. And so, there's some things that you can use, like the cloud, but that's quickly becomes prohibitively expensive. So, one way to reduce this computing load is simply to make your networks more efficient. One way to do this is to have multitask networks. So instead of just identifying the type of interaction, you could identify the number of particles that come out of the interaction, or you could identify the sign, so whether it's a neutrino or an anti-neutrino interaction. And work is being carried out to begin doing that. Obviously, a very easy way of reducing computational load is simply having smaller networks, but they often, have reduced performance, which is far from ideal. It's also possible to simply, more nuanced ways to reduce the number of operations. So that's particularly important for liquid argon TPCs. So as you could, the like of which like Dune is going to be when we start running it in 6 or 7 years. And so here you can see that most of this image here is blank, empty space. So that means that the network is going to be doing lots and lots of calculations where it's adding or multiplying zeros, but next to each other, which is clearly pointless. So you can use submanifold sparse CNNs to only perform calculations when you have non-zero pixels. And it's been found that doing this can reduce inference times by a factor of 30 and the memory cost of evaluation by a factor of 300. Finally, physicists aren't very good at sharing their data. So open data sets are commonplace in data science. They're still really not widely used in particle physics. And this is sort of an artifact of experiments being very worried that someone else will get their data and one up a set of results that they are either in the process of performing or just have performed. So efforts are underway to try and change this. So there's the TrackML challenge, which was initiated by the LHC experiments. So here you can see 10,000 simulated tracks in an LHC detector, and it'd be really great if all of particle physics could move to doing something like this. Open data sets would allow multidisciplinary research, and would inevitably improve the quality and physics reach of our algorithms. But it would require quite fundamental changes to some of the policies of experiments. So I just very quickly wanted to finish on some of the future opportunities offered by machine learning. So machine learning can really help us to control and manage our data rates. So Dune is going to be looking for very rare processes that will be massively dominated by things like radiological backgrounds or electronics noise in their detector. And it's really possible that FPGAs, so field programmable gateway arrays, will be able to really help the detector process all this huge amount of data, and be able to really help siphon off the interesting events without saving petabytes upon petabytes of data to disk. And these things will have to be able to run near continuously, processing terabits of data per second continuously for more than 20 years. So they have to be very, very efficient and very have very high reliability. And the use of machine learning offers the chance to expand the physics program of experiments, and this has already been seen in the LHC experiments. And may help reduce the energy thresholds for some of these searches by an order of magnitude. How can physics contribute to machine learning? So, as I've tried to say, some of the quantitative analysis that we do of our machine learning algorithms, like what we do in Nova, will be really crucial because physicists are natively trying to understand all of this bias that we have, and as it becomes more and more widespread, we're going to be really pushing the boundaries of this. This is particularly important, as machine learning creeps into everyday life more and more. It brings about it, ethical and security concerns, and the problems themselves are very similar to the things that we're trying to grapple with in particle physics. Another key difference is that particle physics uses simulated data sets rather than the actual data themselves. And this means that we can look at how our networks behave under very carefully controlled changes to the training data, or even the evaluation data. And that means that we can really help identify how these minor differences play into the effectiveness of your neural networks. And by comparing the efficacies between the two domains, we can really improve studies in domain transfer. And then finally, there's also we've made advancements in the benefits that providing context to your network provides. So we found that adding contextual information to a particle identification network improved performance. So if you are trying to identify this particle here, we found that by providing that contextual information of the whole interaction itself, improved performance by 11%. And sort of the reason behind this is that looking at just this particle here, I can tell you that it's either an electron or a photon because of how it showers. However, it's very difficult to know exactly which one it is. However, when you pass it the entire event for context, how particles called pi-zeros decay is that they produce two very collinear photon showers. And so this shower here and this shower here are very, very straight and linear with each other towards this point here. And so that means that they're most likely each a photon coming from a pi-zero decay. So this network here was the first to employ a Siamese architecture, particularly primarily to add context to a network. And as we start doing this in different scenarios, we'll obviously find many more synergies between academic and industry applications. And I'm sure this exploration will ultimately improve both fields significantly in the future. So thank you very much for spending your morning listening to me talk. Just in summary, neutrino experiments use a myriad of technologies to study numerous physical processes, and they all apply machine learning in some way, shape or form to do so. Machine learning algorithms have been adapted for a range of applications, including event classification, energy reconstruction, which I didn't cover very much here, but it's being used as well within science to do this. Monte Carlo generation and bias reduction. Many of the challenges arising from applying machine learning have been overcome, though there's still many challenges that remain. And going forward, I think there's a great deal of progress that can be made by merging the applications of machine learning, both neutrino physics and industry. And I've just put a link to the paper where I discuss all of these different strategies and challenges that we've overcome here on the summary, as well as on the first slide. So yeah, thank you very much for listening to me. I hope that it was all understandable.
Thank you very much, Karl, for this very nice seminar. We appreciate the time that you took to share this information with us. Maybe Karl can have some questions if anyone has questions.
Yeah. So Karl, I was wondering. So as you mentioned, most of the deep learning efforts are being applied to these networks are trained on simulations, coming from Monte Carlo simulations. Is there an experiment, training experiment that is already implementing like deep learning techniques on the experimental data, like directly or something like that?
There must be, but I do not remember. Don't remember a specific example. I'm trying to think. Sorry. There must be, but I can't think of a specific example. A specific example, I'm afraid.
Karl, I just
sorry.
want to make sure that it's clear for everyone that the training is done on simulation, but they do apply the techniques to the data to be able to identify real particles.
Oh, right, yeah. Sorry, yeah, I was thinking specifically about training on data. Yeah, every experiment is, performing the evaluation on data. I'll try and have a think, and if I remember one, I'll send the information to Enrico and Alvaro.
Any other question, guys, for Karl? Okay, I think.
So I had just one more question. So basically, on this same topic of implementing deep learning techniques to simulations, I don't know if in your training experiments there has been like a study of how networks also not only learn to classify or reconstruct certain physical parameters, but also like do they learn systematic errors or like things like from the simulation, not like just from the simulation?
Right. Are you sort of asking if they learn about systematic effects that you may pass to the network?
Yeah, from the simulations and not from like actual physical processes.
Yeah. So let me see. If I go to a node, so this is one place where I can talk about Nova much better than anything else. Sorry. Yeah, this will do. Do I have a? Oh yeah, I do. If I go all the way to the start, here. Yeah. Well, yeah, you can sort of see it. So if you focus here on Nova on the left, you can see that the different boxes where the different hits are redder or lighter, depending on the energy that is deposited there. And some of that is related to the calibration that we apply to the detector. So, we read out a hit and we sort of try to figure out how much energy that, that deposition actually corresponds to, depending on, how far down the fiber it was when, where the hit was read out, where the hit was produced. In our latest version of the training, we scaled the calibration, so the sort of the energy of the hits up and down by 10%, according to a Gaussian smear. And by doing that, to sort of accommodate for some of the uncertainties that we had in our calibration, we found that the network efficiency improved by, I think it was about 5% or so. So Nova's sort of the one that I know the most, the most intuitively about. But I think we're doing very similar studies across all different experiments as well. Sort of trying to quantify the effects that different scalings of our pixel maps and things can have on the networks. Does that address the question that you had?
Yeah. So yeah. Basically, and you could you see that these, like, for example, calibration effects, could they be accounted for in the Monte Carlo simulations? So, and I think that's one of the things you mentioned about this process being calibrated to a particular. I don't remember what it was, but where the detector was basically calibrated for a particular with some particular thing, and then when you accounted for this uniform distribution of calibrations, you get like better results. Is this the same thing you're mentioning right now?
I'm trying to remember the second part, where I spoke about the second part of your question. Oh, I think you're on about. Are you on about this?
Yeah, that one. Yeah,
right.
Yeah, that one. Yeah, the calibration source. Yeah, that's what it. Yeah.
So this is similar to that, but it's subtly different. So your first question was about calibration differences in the Monte Carlo. So I mean, again,
right, yeah.
Again, I can talk much more, natively about Nova. So we make systematic samples of the Monte Carlo where we shift the calibration up and down. We shift the light level around. We shift how we do all of our normalizations coming out of the detector, and we use that to produce, have some sort of systematic effect for how our analysis as a whole responds to these changes. Not necessarily just focusing in on the networks themselves. That we're going to start trying to look at that in the future, in the very short-term future. This experiment, though, it's a much finer point about the calibration source that they had. So they trained on a calibration source in their detector. And I forget exactly why. I don't think they sort of determined exactly why, like just training on this calibration source. So like, I guess it may be that this had a very finely peaked energy, but this caused their network to have an unusually large and a good energy resolution, for this particular energy. So instead of training on a single source, they instead trained on a generic gamma radiation source in the center of their detector, and let it decay, decay isotropically with a much larger range of energies. So this is much more about carefully constructing your training data set rather than necessarily looking for systematic pulls one way or the other.
Okay. Yeah, I think it's clear now. Thank you so much.
Great. Yeah, sorry, it's difficult to convey.
Thanks. Yeah, thank you both.